Hi friends, welcome to my channel. Let's have a look at problem 2615, a newly appeared problem, the sum of distances. In this video, we're going to explain a solution based on the treatment, partial sum and binary search. So this problem is marked medium, so actually it's very straightforward if you realize the main point. First, I'll read through the problem statement, and then we digest with the examples. And then we explain the algorithm, and finally we explain the code one by one, line by line. So here we are given a zero-indexed integer array called nums. There exists an array called array of length, the same as the list nums. So where array I is the sum of ij over all j such that nums j equals nums I, and the two indices are different. And if there is no such j, in other words, the corresponding element appears just once. So we set array I to be 0, right? So we want to find this array and return it. So here are two examples. Example 2 is special. The reason is that the list nums contains unique elements. In other words, each element appears just once. So we output 0, 0, 0, right? And then for the first example, so notice that 3 and 2 appears each once. So the corresponding number in array is 0 and 0 for these two elements. Now 1 appears 3 times. The indices are 0, 2 and 3, right? So if we compute this 0 and here is 2, 3, so 2 minus 0 and 3 minus 0 are 2 and 3 respectively, so we get 5. And for the index, for the 1 at index 2, so we have 0 minus 2 absolute value and 3 minus 2, so we get 4, right, in total. Let's see, we get 0 minus 2 and plus 3 and minus 2. We get 2 plus 1, that is 3, right? For the last one, the index is 3. So the previous two have index 0 and 2. So 3 minus 0 is 3. 3 minus 2 is 1. So 3 plus 1 is 4. So we get 4, right? So we have 5, 3, and 4. So this is example 1. So now let's look at the constraints. First, the list nums can have a length up to 10 to the power 5. So this number actually is a decent large number. In other words, when we do the coding, so we need to think of how to effectively compute these sums, right? So distance sums. And then the elements is not that essential. Basically, it's non-negative and bounded above by this 10 to the power 9. So this is for sure a larger number, right? So with that said, basically we are ready to do the analysis. So here our treatment is based on partial sum and binary search. So here partial sum you can understand as a prefix sum or suffix sum. It's essentially the same thing, right? So here I'm going to use example 1 to demonstrate the procedure, right? So basically here step 1 is to partition the indices according to the unique values. So in this example, so we have 3 unique values, that is 1, 2, and 3. So for the value 1, so the corresponding indices are 0, 2, and 3. So we make it a dictionary, right, with the corresponding indices list. And for the unique value 3, so the index is 1. And for the unique value 2, the index is 4, right? And step 2 is compute this distance sum. First, for 3 and 4, so these are occurring just once, right? So the element distance pair would be so 1 corresponding to 0 and 4 corresponding to 0. So here 1 is the index, right? 4 is the index, because our final goal is to get the corresponding distance sum corresponding to the indices essentially, right? Then for the 1, it appears at indices 0, 2, and 3, right? So if we compute the distance sum of the indices absolute difference, right, that is 2 minus 0 plus 3 minus 0, that is 5. So similarly, we can compute for the index 2. So we get 2 minus 0 plus 3 minus 2, that is 3. Similarly, for 3, we get 3 minus 0 plus 3 minus 2, that is 4, right? So we have 0 corresponding to a distance 5, and the index 2 corresponding to a sum of distance 3. Similarly, index 3 has a sum of distances 4. So step 3, so we join and return. So we have 0, 5, 2, 3, 3, 4, 1, 0, and 4, 0. So in list, it's corresponding to 5, 0, 3, 4, and 0, right? But for this problem, so the above procedure basically gives us the sketch, but there are some details. The key point is the computation in 2 here, right? So basically, if a unique value appears many times, so we need to make sure our computation is efficient. So assume that we have indices list, so A1, A2, A3, up to AK, up to AN, right? Here I'm using one indexing just for convenience, right? So for each index AI, right? So we assume that these are sorted, right? Because when we do the scan, the list is naturally sorted. So for the index AI, there are I indices to the left, that is no larger than AI. Then the remainder, let's see, from AI plus 1 up to AN will be larger, right? So the distance sum would be the following. So for the previous one, because they are smaller than AI, so we're going to use AI minus A1, AI minus A2, up to AI minus AI itself. For sure, this produces 0. But let's compute it formally. So this is the first bracket item. So then the later ones, because they are larger than AI, so we're going to compute AI plus 1. So here, I plus 1 is the subindex, right? Minus AI plus AN minus AI. So the former, the first one, is nothing but, so we have I times of AI, right? Then minus the summation of A1 up to AI. So this is the prefix sum. And then the second bracket is the total sum minus the prefix sum, right? This is this term. So minus the corresponding number of AIs, that is n minus I. So we would use prefix sum to do it efficiently. So this is what we are going to do. And this point is actually, we guess, the main point to improve efficiency. So with that said, we're ready to write the code. As for coding, actually, we just need to translate above ideas. So there are many different formats of representation or writing, but for the purpose of exposition, so I'm going to write step by step. So preparation, right? So we're going to partition the indices into lists. So here I'm going to use default dictionary. So the container will be a list, right? Then we're going to iterate over nums. So for I, y in enumerate nums. So y is going to be the key, right? So y, so we're going not y and dy. So if y had appeared before, so because this is the default an empty list, so we're going to append this index, right? So this way we finished the step here, partition. So now let's compute distance, right? So to compute distance, so I'm going to write a utility function, let's see, a hyperfunction. So basically, I'm going to compute for the recurring indices. So given a, so let's write the function signature. I just call this function f to save some typing. So given the indices list, so this array is in sorted order because of this way we iterate, right? So let's see, array in sorted order from small to large, from small to large. So actually, because here in this problem, array will hold the different indices, this array actually is strictly increasing and contains distinct elements, the indices. First, I'm going to track the length of this array, right? If m equals 1, then it just return 0. So we are going to return this. So we're going to return a dictionary. So array of because it contains only one element. So also we will set the value to be 0. So this is the special case. Otherwise, I'm going to make a copy of this array, right? The reason I make this copy is that I want to compute the prefix sum list, right? So here it's very simple, right? So for I in range 1 to m, right? So aux I, this is the prefix sum up to the element array I, right? So what we're going to do is this is aux I plus 1, I minus 1 plus the array at index I, right? So this way we get the prefix sum corresponding to this array, right? So here we wasted some space, but that will be fine. And then we're going to compute the dictionary corresponding to here for each of the unique value and their corresponding lists. So this is actually very simple. So we can use binary search because this array is in sorted order. So it's very convenient. So here we are going to initialize a dictionary, and then we're going to iterate. So for y in array, what we're going to do is to get the index, right? So we are going to use bisect left. This is the array is the iterable or sequence we want to check insertion point. The target we want to check is y. So basically, IDX gives how many items in array is less than this index y, right? So basically, I want to make a check. If IDX equals 0, it means that all the indices in the array is no less than the y. In other words, y will be the first index. So in this case, so we are going to set dy to be the sum, right? The total sum. So minus this first index, that is m times y. So this will be the the sum of distances in the sense of absolute value for index differences. So this is the one case. Else, so we want to consider this in this else block, IDX will be greater than 0, at least 1. But we know that y is in array, right? So we can be sure because we are calling bisect left. This y actually is less than the length of this array, m, right? But that's a small point. So in this case, we are going to set this y. So there will be IDX terms that is less than y. So for that part, we are going to do this IDX minus y minus the prefix sum up to this IDX minus 1, right? So notice the indexing here, right? So that's the point. So now we are going to compute. So this is the first bracket in above, corresponding to here, right? So this corresponds here. So next we compute the tail, right? So that is aux -1 minus aux IDX minus 1. Then, so we're going to, because this term corresponding to terms that are larger than the index y, then we're going to minus y times the count, that is m minus IDX, right? So this way, for each index in this array, we get this their corresponding sum of distances. So what we are going to do is to, let's see, we write here, return this d. So that's the main work here. So once we have this function, then we just need to do the join and prepare the return. Let's see, prepare the return. This is actually very straightforward. What we're going to do, let's initialize a result called dictionary, because each partition of the list in this dictionary contains a subset of indices. We want to join this result for all the subsets. So this is very simple, right? So for array, in D values, right? That's individual sublists. And then we're going to do this result union with this F array, right? Because F returns the dictionary, right? We join these dictionaries, right? And then we can do the return, use a list comprehension. That's actually very convenient. So because the problem requires us to return a list of integers, right? So we're going to do result I. So I will be the keys, right? For the key will be in range M, right? So let's see, did we let me use length of nums, right? So with that done, basically this short code forms a solution format to this problem. So before we make any comments, let's first do a check. Yeah, it passes one test case. Now let's look at the generic case. Yeah, it passes all the cases. So here, let me give a quick summary about the structure. So in this video, or in this solution here, so we used partial sum and binary search. So both actually play the role of accelerating the overall procedure, right? So in the specific coding, actually we divided into 3 parts. So once we grasp the main idea, so the 3 steps are actually very routine. So first, we make some preparation. In other words, we partition the indices. And then in the second step, we wrote a hyperfunction or utility function so that for each of the partial index list, we can compute the sum of distances. And then in the third step, we prepare the return. So first, we join the things in the form of dictionary. And then we use list comprehension to make the format aligned with the problem requirement. And finally, we test the solution. So that's about it for this specific problem and this video. If you find the explanation here is of use, you are welcome to follow up me in YouTube or share with your friends. With that said, I guess that's about it for this video. Thank you.